Whenever you're just refreshing your feed or streaming a movie, have you ever really stopped to think about what's holding all that together? It feels instant, like magic, right? But it's not. It's actually a massive, invisible fortress of code. And today, we're going to peek behind the curtain and look at the core principles that keep it all from just poof, falling apart.
So that's the big question, isn't it? How do these digital giants, the YouTubes, the Netflixes of the world, handle billions of us every single day without just crumbling? They're under constant attack, constant pressure. It's one of the highest stakes engineering puzzles out there.
And to get a feel for the scale we're talking about, let's just start with something like a major news feed. We're looking at maybe 10 million people using it every day. And every single one of them expects it to be fast, personal, and always up to date. That's a huge ask.
But then you look at a platform like YouTube, and the numbers, well, they're just on another planet. We're talking 5 billion video views every single day. Just try to imagine the sheer volume of data flying around every second to make that happen. It's honestly mind-boggling.
And this is where it gets a little scary. At this scale, one tiny mistake, one little crack in the armor, can lead to a total disaster. A single point of failure doesn't just mean a temporary glitch. It could bring the whole system crashing down, affecting millions of people and maybe even losing our data for good.
So with stakes that high, how do engineers even begin to build something secure? Well, they don't just start coding and hope for the best. They start with a simple, really elegant, and incredibly powerful framework. It's kind of the North Star for building secure systems, the CIA Triad.
First up is C for confidentiality. Think of this as your digital privacy. It's all about making sure that only the right people can see the right information. Bottom line, it's about keeping your private stuff, well, private.
Next, we have I for integrity. This is all about trust. It's the guarantee that the data you're looking at is the real deal, that nobody's messed with it, either on purpose or by accident. I mean, when you check your bank account, you need to know for sure that the number you're seeing is accurate. That's integrity.
And finally, we have A for availability. This is the one we, as users, probably notice the most. It just means the service is up and working when we need it. Because, let's be honest, a system isn't very useful if it's always down, no matter how secure it is, right?
All right, so we have our 3 pillars. Now let's really dig into the first one, confidentiality. How do these massive systems actually keep our secrets safe? It's not just one thing, it's an entire arsenal of techniques working together.
What's so cool here is how these different methods build layers of security. First, authentication proves you are who you say you are, often with something called an auth token. It's like a temporary digital backstage pass. Then, HTTPS creates a secure encrypted tunnel for your data to travel through so no one can listen in. The data itself is also scrambled using powerful encryption like AES. And for really specific things, like uploading a file, the system can create a special pre-signed URL that works just once for a short time, which is a super secure way to grant temporary access. Okay, so we've got our secrets locked down, but how do we know that data itself is trustworthy and hasn't been corrupted? That's where integrity comes in. And for giant systems spread all over the world, this is a seriously tough problem to solve.
This process it's just brilliant. To make sure data doesn't get lost, it's copied, replicated in multiple physical locations. But then you have a new problem. How do you keep all those copies in sync? That's where versioning helps. Every change creates a brand new, unchangeable version. And then, to quickly check if all the copies match, systems use this incredibly clever tool called a Merkle tree. Instead of comparing 2 massive books word for word, it's like you just compare a unique fingerprint of each chapter. It lets you spot a difference almost instantly without moving tons of data around.
And that brings us to our final pillar, availability. How do services we rely on stay online 24/7, even when things inevitably go wrong? Well, the number one enemy here is something called the single point of failure. This quote, it just nails it. If your entire operation hinges on one single piece of hardware or software, you're basically living on borrowed time. The whole goal of designing for high availability is to hunt down every single one of those weak links and eliminate it.
So how do you do it? You build in redundancy at every level. You might start with one server, but that's risky. So you add a load balancer to spread the traffic across a bunch of servers. Then you copy your database, so if the main one goes down, a backup is ready to take over instantly. And for the ultimate protection, you replicate your entire setup in different data centers across the world. That way, if a whole region has an outage, traffic just gets rerouted, and for you, the user, you never even notice.
Now, here's where things get really, really interesting. Because these three pillars, confidentiality, integrity, and availability, they don't exist in a vacuum. In the real world, they're constantly pushing and pulling against each other. It's a delicate balancing act.
And here's the absolute truth of it. There is no such thing as a perfectly secure system. It's a myth. Every single design choice is a trade-off, a compromise you have to make between these competing goals. Let's look at a real-world example of how this works.
Okay, this chart looks a little intense, but trust me, the idea is pretty simple. Imagine your data is copied onto, say, 3 different servers. Let's call that number n. To write new info, you need a certain number of those servers to agree. We'll call that W for write. And to read info, you need to hear back from R number of servers for read. Now, if you want your app to feel super fast when people are reading, like scrolling a feed, you can set R to 1. Just grab data from the first server that responds. But to guarantee that data is correct, to maintain integrity, you have to make your write slower and require that all 3 servers confirm the new data. That's the column on the left. Fast reads, but slower writes. You literally can't have both be the fastest.
And that's the absolute heart of system design. Every choice has a consequence. Do you tune your system for lightning-fast writes? Maybe for something like a stock trading platform. Or do you prioritize instant reads for an app where people are mostly just consuming content? It's a constant balancing act between the pillars of the CIA Triad.
So the next time you post a photo, or stream a song, or check your bank account, just think about this for a second. Is the service almost never down? Does new information show up instantly for everyone? Now that you know the framework, you can actually start to see the invisible choices that engineers made. What trade-offs do you think are shaping your favorite apps?